Okay, so good afternoon, everyone. Myself Adira, and I'm a PMR scholar from IIT Madras, and I'll be your TA for the course Chemistry of Main Group Elements. And I'll be discussing about the assignments from previous year and ongoing course. Um, this session is mainly for clarifying your doubts regarding the assignments, and since the assignment 1 and 2 is still open for submission. I will not be discussing about it, but I have chosen similar questions from previous years and same concepts so that you can solve the assignment easily, and you can ask any doubts directly by unmuting, or you can type it in the chat box. So if you miss this lecture, no problem. Like you'll have another interactive session on Tuesday evenings by another TA. So similar content will be shared there as well. So the um, lecture is recorded, so it will be shared with you, and all the slides also will be shared. So let's start. The question number 1 is. The IUPAC name of the unknown element having atomic number 147 is, and option number A is unanium, B is untriquadium, C is unquadseptium, and D is unquadoctium. So for naming any element, we should know how each number is represented. So this is how each number is named. For 0, it's nil. For 1, it's un. And 2 is bi. 3 is tri. 4 is quad. And 5 is pen. 6 is hex. 7 is sept. 8 is oct. And 9 is n. So for an example, if we have an element like 157, it will be 1 is un, 5 is pent, and 7 is sept. And at the end of it, you will have to write IUM. So here it's 147. 147. 1 is un, 4 is quad, 7 is sept. And the name will be unquad septium. So the option number C is the answer. Do anyone has any doubt, or is it clear? Ankita or Aparna? Okay. So the next question is correct electronic configuration of rubidium, which has an atomic number of 37. Option A is neon and 4s1, B is argon and 5s1, C is krypton and 5s1, and D is xenon and 5s1. So for writing electronic configuration of any element, we can write it with one nearby inert gas and the rest of the electrons. So we need to know the periodic table so that we'll be able to recognize which inert gas is closer to rubidium, which has atomic number of 37. So in this periodic table, in inert gases, first one is helium, which is having an atomic number of 2. Next is neon, which has number of 10. Next is argon, having 18. And next is krypton, which is having 36. And next one is xenon, having 54. And our uh, element of interest is rubidium having atomic number 37. So for 37, the nearby inert gas is krypton. So krypton is the nearby inert gas. So the answer will be option C, krypton, and 5s1. So 5s1 comes from, since krypton is 36, one more electron is required to make become rubidium. So it's krypton and 5s. And the next question is the IUPAC name of the unknown element having atomic number 120 and its electronic configuration are. So it's given inert gas element 118 is Organson, represented as Og. So the options are unbinilium Og5s1, B is unbinium Og5s2, C is unbinium Og5s1, and D is unbinilium Og5s2. And so this is a combination of first and second question. So the atomic number is 1, 2, 0. So it is un, 2 is bi, and 0 is nil. So the IUPAC name will be unbinilium. So there are two options with unbinilium, and we are given inert gas element 118 is Og. So it will be Og, and to become 118 to 120 we need two more electrons. So it will be Og 5s2. So it's option D is the answer. So the next question is arrange the set of chemical species in the increasing order of electron affinity, and the elements are carbon, silicon, and germanium. So electron affinity is the energy released when one electron is added to one atom in its gaseous state. So if the element is small, the energy, that is electron affinity, will be really high, and if the atom is really large, then electron affinity will be reduced. So the options are given: germanium is less than silicon less than carbon, and second one is carbon less than silicon less than germanium. C is germanium less than carbon less than silicon, and D is carbon less than germanium less than silicon. So carbon, silicon, and germanium, they are in the same group, that is in carbon group, carbon, silicon, and germanium. So this is the order. So in a periodic table, when we move across the period, the size of the elements decreases, so the electron affinity increases. So, and while moving down the group, the atomic sizes increases, so electron affinity decreases. So since this the order of increasing atomic size, so the electron affinity should be decreasing in this order. That is, carbon will be having higher, then silicon, then germanium. So the option is this one. So just reverse this one. So germanium is less than silicon less than carbon. So option is A. And the fifth question is arrange the set of chemical species in the decreasing order of electron affinity. Chlorine, Cl plus and Cl minus. So options are Cl minus greater than Cl greater than Cl plus. B is Cl plus greater than Cl greater than Cl minus. C is Cl greater than Cl minus greater than Cl plus, and D is Cl plus greater than Cl minus greater than Cl. So here we are given three species: chlorine, Cl plus, and Cl minus. So how do we get to Cl plus? Cl will be when we remove one electron, it will become Cl plus, and when we add one electron to Cl, it will become Cl minus. Cl plus one electron will give Cl minus. So when we convert an atom, that is neutral atom, into its cation, the size will be decreasing. So Cl plus has size will be lower compared to Cl, because the effective nuclear charge will be higher for Cl plus. So the number of electron is less in Cl plus. So the nucleus will attract electrons more tightly in Cl plus compared to Cl. And in Cl minus, the case is since we are adding one more electron to Cl, the size of the species becomes large, because the effective nuclear charge will be reduced. So Cl minus charge, that size is largest for Cl minus compared to Cl. So the dependency of electron affinity and size is proportional to 1 by size. The bigger the size, electrons affinity will be lower. So the order of size is Cl plus less than Cl less than Cl plus. Sorry. Uh, Cl plus less than Cl less than Cl minus. So the electron affinity will be the reverse order. Uh, the order of size, increasing order of size. So this will be the reverse order of electron affinity. That is, Cl plus will have higher electron affinity compared to Cl minus. So the answer is option B, Cl plus greater than Cl greater than Cl minus. And the next question is the screening constant and Z effective value for 2p electron in oxygen, which is having atomic number 8R. So for this, we need to know the concept of screening constant and the effective nuclear charge. So uh, yeah. If we have an element, it will have a nucleus containing proton. Normally, it will be the atomic number, and the nucleus will be surrounded by uh, electrons. So if we have electrons, So if this the first shell, this is the second shell, the nuclear charge will be attracting these electrons, and the mm, extent of attraction will be different for different shells. That is, the extent of nuclear charge acting on this uh, electron closer to nucleus will be higher, and moving away from the nucleus in each shell, the effect of nuclear charge will be lesser and lesser. And it's because of the electrons present closer to this nucleus. They can actually uh, shield some of the nuclear charge from the nucleus, so it won't go uh, to like all of the nuclear charge won't be able to attract the electrons in its outer electrons. So to calculate the shielding effect, uh, we use Slater's rule, and for each uh, orbitals, the uh, shielding constant will be different. So for case 1, it's S and P electrons, and Slater's rule says that electrons in same shell shields 0.35. That is the uh, outer electrons. Like if this is the outer electron, uh, and the electrons in this shell will shield 0.35, and the next one, that is inner uh, shell, which is having n minus 1, and they will shield 0.85, which is 0.85 is higher than 0.35, and then n minus 2, the next inner shell, it will shield 1, and going closer to nucleus, the shielding constant will increase. And the case 2 is for d and f electrons. Electrons in same shell will shield 0.35, and all the inner shells will shield 1. So let's calculate the screening constant and effective Z value. For this, uh, Z effective is Z minus screening constant. So we need to calculate screening constant, so that screening constant of 2p. So to calculate screening constant, first we need to know the electron configuration of oxygen. So oxygen is having 8 electrons. So it is 1s2, 2s2, 2p4. So so n, and we have n is 2, since we are asked to calculate for 2p electron, and we have n minus 1 as 1. So we can calculate the shielding constant. So, we have 3 electrons in 2p, and since we are asked to calculate Z effective for only 1 electron, we can split this as 2p 3 plus 2p 1. So if we are calculating for this 2p1, there is 3 other electrons in 2p. So from this one, electrons in same shell will be 0.35. That is 0.35 into 3 for 2p plus there is 2 electrons in 2s. So electrons in same shell again 0.35, that is 0.35 into 2 plus in n minus 1 shell it's 0.85. So total will be 0.35 s equal to 3.45, and z effective is z minus s, that is z is given 8, so 8 minus 3.45, that is 4.55. So the answer is option B. Is it clear? Anyone have any doubt in this one? So if you have any doubt, you can ask in the chat box. So and I'll move on to next question. So the next question is Z effective value for p electron in boron. So similar to previous one, we need to know the electronic configuration for boron. Boron is 5, that is 1s2, 2s2, 2p1. So first we calculate the screening constant. So n is 2 and n minus 1 is 1. So screening constant for 2p is given as there are 1 electron in 2p. Oh, so 1 into 0.35 plus there are 2 electrons in 2s, but it's in same shell. So 2s and 2p are in same shell. So it is 2 into 0.35 plus there are 2 electrons in 1s. So 0.85 into 2. So the total will be 2.4, and Z effective will be Z minus S. So Z is 5 minus 2.4. That will be 2.6. So option A is the answer. So the next one is similar question, but for 3D electron. So we need to know the atomic number of bromine. Bromine is 35. So it's 1s2, 2s2, 2p6, 3s2, 3p6, then 3d10, 4s2, 4p5. So we are asked to find Z effective for 3D. So we can neglect whatever electrons are coming after this 3D. So we have to calculate shielding constant till 3D10. So for D and F electrons, the rule is electrons in same shell shields 0.35 and in lower shell shields 1. So there is 3D is N, and we'll consider these as lower. So in 3D 10, that will be 3D 9 plus 3D 1, because we are considering only for effective uh, nuclear charge only for one electron of 3D. So we'll have to calculate for rest of the 9. So here we'll calculate n is 3, n minus 1 is 2, and n minus n minus 1 is 1, and n minus 2 is so n minus 1 is 2, and n minus 2 is 1. So S of 3D is given as for there are 9 3D electrons. So uh, 9 into 0.35 for 3D, and there are 8 electrons in 3s and 3p. 8 into 1, then in S2 2s and 2p there are 8 electrons again, plus there is 1s and it has 2 electrons. So 2 into 1 for 1s. So screen constant for 3D will be total of 21.15, and Z effective is Z minus S, that is 35 minus 21.15 equal to 13.85. So option D is the answer. Anyone has any doubt in this one? If not, let's move on. So the decreasing order of ionic radii for the given isoelectronic species is. So the options are given as N3 minus, Na plus, Mg2 plus, and O2 minus and F minus. So 5 species are given, and they are isoelectronic. We can find it from this periodic table. So nitrogen, oxygen, fluorine, and these three, and sodium and magnesium. So isoelectronic species are species having same number of electrons in the same number of electronic configuration. So here uh, we are asked to find decreasing order of ionic radii. So when we move from left to right of a periodic table, the ionic radii actually decreases because of the increase in effective nuclear charge. And when we move down the group, the radius of elements increases. So also we need to note that when elements are having negative charges, that is like anions. Anions will be having larger radius because of the repulsion between the electrons, and the effective nuclear charge will be lower for anions. And for cations, the effective nuclear charge will be really high. So the size of the element or species decreases. So, and as the charge increases, if its negative charge is increasing, the size will be increasing. If the positive charge is increasing, the size will be reducing. So there are uh, 5 species given, and from the periodic table, we know that nitrogen will be having larger radius compared to oxygen than compared to fluorine. And between sodium and magnesium, sodium will be having a higher radius compared to magnesium. But there are ionic species here. So since nitrogen has 3 negative charges, it will be uh, having larger radius compared to others. Then the next element with next lower number of uh, negative charge will be in next. So it will be O2 minus. Next will be next ion, that is F minus. So between sodium plus and magnesium 2 plus, we need to know which one is small. So magnesium has 2 positive charges. So it will be having lower ionic radius. So sodium, the order is so sodium plus will be having larger radius compared to magnesium 2 plus. So the answer will be C. And the next question is the correct quantum number set for the electrons present in 2s orbital of F atom is. And options are given as n equal to 2, L equal to 0, ML equal to 0, MS is plus or minus half. So the changing values are for N, L and ML are given. And so we need to know 4 uh, quantum numbers, and they are principal quantum number, orbital angular momentum quantum number, magnetic quantum number, and spin quantum number. So principal quantum number is the denoted as n, and it is the electron shell of the electron we are considering. So here given as 2s, so n will be 2, and it generally n will have values from 1 to 3, and only positive integers, uh, and it denotes the electronic shell. And next one is orbital angular momentum, L, and it denotes the number of nodes in an orbital. And L varies from 0 to n minus 1. And for s orbital, it is 0. For p is 1. D it's 2, and for F it's 3. So in question we are asked to find for S, and so for S L is 0. And next one is magnetic quantum number ML, and it gives the orientation of orbital. That is ML. It varies from 1 to L to minus L through 0. That is, if you have L equal to 1, then ML will be minus L, plus L, and 0. So from minus L to L through 0. And here we are given S orbital. So since L is 0, ML will be 0. And next one is spin quantum number MF, and it denotes the direction of electron spin, and it's either plus or minus half, and it's independent of all other quantum numbers. So electron can have either plus half or minus half. So n for 2s orbital of F atom, it is n equal to 2, L equal to 0, and ML equal to 0. MS is plus or minus half. So the option A is the uh, correct answer. Anyone has any doubt in this one? Okay. So moving on to next question, the bond angle in IF7 are 120 and 90. All are 90, 90 and 72, and the last option is 85 and 120. So from VSEPR theory, we'll be able to find out the geometry and uh, structure of IF7, and uh, so if we consider I as the central atom, uh, it's in the halogen group, and halogens have 7 valence electrons. So 1, 2, 3, 4, 5, 6, and 7 electrons in its valence, and it is bonded to 7 fluorine atoms. So if we calculate steric number, it will be 1, 2, 3, 4, 5, 6, and 7. That is all are bond pairs. So if we have all bond pairs and steric number 7, the geometry will be pentagonal bipyramidal. So it will be iodine is the central atom. So 5 bonds in the equatorial position, and 2 bonds in the axial position. So in a pentagonal bipyramidal, the angle between this equatorial position will be 72 2 degree, and between axial and equatorial will be 90 degree. So the answer will be option C, 90 and 72. And the next question, the correct order of the effective nuclear charges. And given 1s greater than 2s greater than 3s greater than 2p, b is 1s greater than 2s and 2p nearly in same energy, and uh, it's greater than 3s. C is 1s greater than 2p greater than 3s greater than 2s, and D 3s greater than 2s greater than 1s greater than 2p. So for this, we can use the Slater's concept, where we calculate the shielding constant for S and P electrons. So uh, in Slater's rule, it says electrons in same shell shield 0.835. In n-1, it shields 0.85, and in n-2, shields 1. That means uh, when we move away from the nucleus, if this one is the nucleus, this is the, if this one is n, this one is n-1, this n-2, given this electrons in n will shield 0.35, in n-1 it shields 0.85, and in n-2 and below it shields 1. So the shielding is really high when we move inside the shells. So as the n increases, the shielding and effective nuclear charge will be reduced. So Z effective is Z minus S. So as we move more, we'll have to add more shielding. So the effective nuclear charge will be reduced. So for oneness, it will be high, and 2s and 2p will be nearly equal, because we are for Slater rule, we are stating for both s and p. So 2s and 2p in similar energies, and 3s will be having lowest nuclear effective nuclear charge. So the option B is the answer. And next question is correct order of electron affinity for species N, P, and AS is. So these elements are in same group: nitrogen, phosphorus, and us. So we are asked to find the electron affinity order. So when we move down the group, the electron affinity will be reducing, since the size and effective nuclear charges size is increasing and effective nuclear charge is decreasing. So uh, electron affinity will be decreasing down the group. So the option will be option A, and having nitrogen having higher electron affinity than phosphorus than us. Next question is correct order of second ionization energies. So for calculating ionization energy, we'll need to know the electronic configurations, and the ionization energy increases when we move along a period, and when we go down the group, ionization energy decreases, because ionization energy is the energy required to remove one electron from an isolated gaseous species. So when we move down the group, the size of the elements is uh, increasing, so the effective nuclear charge is decreasing down the group. So it's easier to remove one electron from larger elements compared to smaller ones. So when we move down, size increases, so ionization energy decreases. So IE is proportional to 1 by size again. And in a period, when we move from left to right, the size is reducing because effective nuclear charge is increasing, and hence it becomes difficult to remove electron from the valence electron. So for the first ionization energy, fluorine, oxygen, nitrogen, and carbon. So fluorine is the smallest in the period. If we write it in the order present in periodic table, carbon, nitrogen, oxygen, and fluorine. So here it is size decreasing. So first ionization energy is expected to be higher for fluorine. So it's be highest, uh, high, and lowest. And here nitrogen is half filled stable, and that is 2p3 configuration. So it will be difficult to remove one electron from half filled configuration. So it will be higher than carbon. And when we move to second ionization energy, carbon will be the lowest, and for nitrogen uh, it will be low, but here first it was 2p 4, and in first ionization energy it will become 2p3, which is half filled stable. So to remove one electron from half filled stable species will be difficult. So this will have highest, and this one will be high. So the order will be O greater than F greater than N greater than C. The answer is option B. And in the next question, the steric number Sn, which is represented as Sn, and the number of lone pairs LPs present in pH 3 are. So option A is Sn steric number equal to 2, lone pairs equal to 1. B is steric number 4, lone pairs 1. C is steric number 8, lone pairs 2. D is steric number 6, lone pairs 2. And so we are given pH 3. So let's consider phosphorus as the central atom, and it's in the nitrogen group. So it will have 5 valence electrons. and it's bonded to 3 hydrogen atoms. So 1, 2, and 3. So this will be the these two becomes one lone pair and 3 bond pairs. So steric number is equal to uh, bond pairs plus lone pairs. So we have 3 bond pairs and 1 lone pair, that is 4. So the answer will be steric number is 4 and lone pair equal to 1. And similarly, next question, the steric number and the number of lone pairs of present in IF2 minus R. So first option is steric number 10 and lone pairs 4. Steric number 4 and lone pairs 2. Third one is steric number 5 and lone pairs 3. Fourth one is steric number 8 and lone pairs 3. So in IF2 we can take iodine as the central atom. So iodine, it's in the halogen group. So it will have 7 valence electrons. 2, 3, 4, 5, 6, and 7. And given a negative charge. So we can add that negative charge as 1 electron to uh, central iodine, and 2 F are bonded. So 2 fluorine atoms bonded. So we have 2 bond pairs, 1, 2, and 3 lone pairs. So steric number is bond pairs plus lone pairs. That is 2 bond pairs and 3 lone pairs. So steric number 5 and lone pairs 3 is the answer. In the next question, the geometries of I3 plus and SF2 molecules respectively are. So given linear and tetrahedral, trigonal, planar, and linear, both linear and both tetrahedral. So we can start with I3 plus. So iodine as the central atom, and it will have 7 valence electrons, but it is given there is a positive charge. So we can include that positive charge to the central atom. So it will become 6 valence electrons. So from 7 valence electron, if we add 1 positive charge, that is, if we make 1 atom, that 1 electron will be removed and there will be 6 valence electrons. And two iodines are bonded to the central atom. So one I and the second. So this one has 2 lone pairs and 2 bond pairs. Steric number is 2Vp plus 2Lp, that is 4. So 4, the geometry will be tetrahedral. So we'll have a tetrahedral for this one. And second one is SF2. And for SF2, sulfur has 6 valence electrons since it's in the oxygen family, and 2 fluorine is bonded to sulfur. So again 2 lone pairs and 2 bond pairs. So steric number will be 4. So again it's tetrahedral. So the geometry will be both tetrahedral. And The next question is the geometry and shape of xenon and bonded to 4 fluorine, XeF4, and option is octahedral and square planar, B is octahedral and square pyramidal, C is octahedral and seesaw, D is trigonal bipyramidal and seesaw. So XeF4, xenon as the central atom, and we have 4 fluorine atoms bonded to xenon. So we have steric number equal to 2 lone pairs plus 4 bond pairs, that is 6. So expected geometry will be, since it's 6, it will be octahedral. But we have lone pairs and bond pairs. So in a system like this, BSEPR theory states that the lone pairs are placed such that there will be minimum repulsion between lone pairs and lone pairs. So it will be octahedral, having octahedral geometry. And the lone pairs will be placed as far as possible. So there won't be any repulsion. Like will be the repulsion will be minimum. So the shape will be square planar. So option A is the answer. And next one is SF6 and PCl5 molecules are given, and find the hybridization. So sp3d and sp3d3, B is sp2d2 and sp3d, C is sp3d2 and sp3d, and D is sp2d2 and sp3d2. So to find hybridization, we need to know how many bond pairs and lone pairs are present. So for SF6, first sulfur in oxygen group, so 6 valence electrons, and 6 fluorine atoms are bonded. So 6 bonds are formed between sulfur and fluorine. So since this one is completely bonded, and steric number will be 6. So since there are 6 bonds, we'll need 6 hybridized orbitals. So it will be sp3d2. So total of 6 hybridized orbital will be there in sp3d2. And for PCl5, phosphorus is in the nitrogen family. So 5 valence electrons, and it's bonded to 5Cl. So for 5Cl, there are 5 bonds formed. So we'll need 5 hybridized orbitals to accommodate these bonds. So steric number is 5. So it will be sp3d, total of 5 hybrid orbitals. So the answer is option C. And the next question is the correct order of hybridization of central atoms in H2, BeH2, XeF2, SiF6 2 minus S. So options are sp3, sp2, sp3d, and sp3d2. And for H2O, oxygen is the central metal. It has 6 valence electrons, and 2 hydrogen are bonded. So it has uh, 2 lone pairs and 2 bond pairs. So steric number is 2bp plus 2lp, that is 4. So 4 hybrid orbital will be required to accommodate 2 lone pairs and 2 bond pairs. So it will be sp3 hybridization. And next one is BeH2. So beryllium has only 2 valence electrons. So it will form 2 bonds with 2 hydrogen. So it will be a linear molecule, and steric number is 2 since only 2 bond pairs are present. And for to accommodate 2 bond pairs, only 2 hybrid orbitals are required. So hybridization will be sp. Next one is XeF2. Xe xenon has 8 valence electrons, and it's forming bond between 2 fluorine. So steric number will be 2 bond pairs and 3 lone pairs. So total of 5. So it will need 5 hybrid orbital to accommodate all these 3 lone pairs and these 2 bond pairs. So we sp3d2. It will be sp3d. Yeah, it will be sp3d because it will be a total of 5 hybrid orbitals. And next one is SiF6 2 minus. So silicon is in the carbon group, and since there is 2 negative charge, we can add as on the central metal as 2 electrons. So 4 plus 2, 6 electrons will be present. 3, 4, 5 and 6. And if we form bond between 6 fluorine, so steric number is 6 bond pairs. So to accommodate 6 bond pairs, we'll need 6 hybrid orbitals. So it will be sp3d2. So option C is the answer. And next one is arrange the following chemical species in the order of decreasing radius. So here sodium, magnesium, argon and phosphorus. They are in the same period. So when we move along a period from left to right, the size of the elements decreases. That's atomic radius decreases from left to right of a period. So we need to arrange these elements in the increasing order of their atomic number. So it will be sodium, magnesium, phosphorus and argon. So we are asked to find the decreasing order of the radius. So smallest will be argon, and then phosphorus, then magnesium and sodium. So it will be sodium greater than magnesium greater than phosphorus greater than argon. Next one is I minus, Ba2 plus, cesium plus and xenon. So these are isoelectronic species. And xenon is the inert gas, and iodine is having atomic number 53. This one is 54. Then iodine is given as iodide, which is having a negative charge, and then barium as barium 2 plus, cesium as cesium plus. So when in group of isoelectronic species, uh, it's always seen that the anion will be having higher radius. Anion will be having higher radius compared to neutral than uh, cations. So cations will be the smallest one in isoelectronic species, and as the charge of the cation increase, size will be decreasing. So in this one, barium 2 plus will be the smallest one, then cesium, uh, then xenon, then iodide. And in this one, carbon, aluminum, fluorine, and silicon. So in the periodic table, carbon and fluorine are in the second period, and aluminum and silicon are in the third. So if we move from left to right, size will be decreasing, and when we move down, size will be increasing. So from this one, we can find that aluminum will be having higher radius than silicon, since they are in the third period, and aluminum comes before silicon. So aluminum has larger radius compared to silicon, then carbon, then fluorine. And the fourth one is argon, K plus, Cl minus, and S2 minus. So again, these are isoelectronic. And so if we go with this concept, anion having higher radius, and if the charge of the anion is higher, it will have higher radius. So among Cl minus and S2 minus, S2 minus, uh, S2 minus will be having larger radius than Cl minus, and between neutral and cationic species, neutral will be having larger radius. So argon and potassium. So the next question is, arrange the following chemical species in the order of increasing order of first ionization energy. So first one is potassium, calcium, and rubidium. So the atomic numbers are 19, 20, and 37. It is in the periodic table, potassium and rubidium are in the same group, and um, potassium and calcium are in same period. So when we move this way from left to right in a period, ionization energy increases, and when we move down the group, decreases. So the order will be higher for calcium, uh, calcium will be higher, then potassium, then rubidium. And here krypton, helium, and argon. So these are inert gases, and the atomic numbers are krypton is 36, helium is 2, and argon is 18. So when we move down the group, ionization energy decreases. So higher will be for helium, then argon, then krypton. So and the next one is uh, iodine, having atomic number 53, and xenon is 54, and cesium is 55. So so in this one, iodine have a electronic configuration of p5. This is p6, and cesium has s1 p0. So first ionization energy will be lower for cesium, since uh, it's easier to remove one electron and become inert gas. So cesium is the lowest, then iodine, then xenon. Xenon has the highest because it's completely filled, and it will be really hard to remove one electron from its p orbital. And in the last one, antimony, tellurium, and tin. So in antimony, its atomic number is 57, tellurium is 52, and tin is 50. So the configuration will be P3, P4, P2, P4, and PP. So it will be difficult to remove one electron from antimony because it has a half-filled stability. So it will be higher. Then tellurium, then tin. And the next question is, what happened to the size of A when it is transformed to A plus, that is formed a cation, or A minus, that's an anion. So when we form an anion from an element A, we add one electron, so an anion is formed. So the effective nuclear charge will be low, which means size will be high. And when we form a cation, we are removing one electron from the element. So the effective nuclear charge will be high. So size will be reducing. So option B is the answer. Element A will be having higher radius compared to cation, and the anion will be having higher radius compared to the element. So that's the end of this lecture. So if you have any doubts, you can ask me. So if you have any doubts from the lecture or from the these assignment questions, you can ask. So basically, in this class, we have discussed about how effective nuclear charge is calculated. Next one is IUPAC nomenclature. Then ionization energy, um, electron affinity, then size of elements, then geometry and shape of uh, molecules using VSEPR. Then so we have covered almost all questions from these five. And if you have any doubts or need any clarification, you can ask. So if you want, we can go through this quickly. So first, the IUPAC name of unknown element having atomic number 147. So basically, we need to know how each number is named. So 0 is nil, 1 is un. So for each number, we have naming. So for 147, it will be 1. We have 1 as un and 4 as quad and 7 as sep. And at the end of the nomenclature, you will have to add IUM. So the nomenclature for 147 will be unquad septium. So option C is the answer. And the next one is electronic configuration of rubidium 37. So for finding the electronic configuration of an element, we write it in terms of inert gases, and since rubidium is 37, the nearest inert gas will be krypton having atomic number 36. So the electronic configuration will be krypton 4s1, krypton 5s1. So and next one is similar to first what we have done. 120, 1 is un, 2 is by, and 0 is nil. So name is unbinilium, and we are given for 118 uh, the element is again represented as OG. So to get to 120 from 118, we will need 2 more electrons. So we have to add 2 electrons. So the answer will be unbinilium, and Ogensen 5s2 is the 120. And next one is arrange the set of chemical species in the increasing order of electron affinity. And we are given carbon, silicon, and germanium, and they are in the same group. And when we move down the group, the size of the elements increases and electron affinity decreases. So electron affinity is directly proportional to 1 by size. So if we have larger size, electron affinity will be low. So carbon is the smallest, so carbon will be having highest affinity. So carbon, then silicon, then germanium. Carbon having higher, then silicon, then germanium. So the answer is A. And next one is arrange the set of chemical species in the decreasing order of electron affinity. And here chlorine, Cl minus and Cl plus. If we remove one electron, it becomes a cation, and cations have smaller size. And if we add one electron, it will become Cl minus. So it has the larger size compared to neutral atom. So chloride ion will be having larger radius, and then Cl plus will be the small. So we are asked to write in decreasing order. So the order will be Cl plus less than uh, Cl plus will be having higher affinity than Cl, the electron affinity order. So Cl plus will be having higher affinity compared to neutral species, then the anion will be having lowest affinity. So the next one is screening constant and Z effective nuclear charge calculation for 2p. a 2p electron of oxygen, and we have Slater's rule, and Slater's rule says that for SNP electron, uh, if the electrons are in same shell, it will be having shielding of 0.35, and when we move inside, for n minus 1 it's 0.85, and for n minus 2 and below shells it will be 1, because as we move inwards of the shell, uh, the shell is closer to nucleus, and it will be they the inner shells will be experiencing more nuclear charge compared to those outside. So the shielding will be increasing when we move inside the shells. And we have calculated the screening constant first, then effective nuclear charge. So from this rule, we have found the shielding constant for 2p. First, we wrote down the electronic configuration of oxygen: 1s2, 2s2, and 2p4. And for each 2p, 2s, and 1s electron, we assign these shielding constants, and found the shielding constant for 2p, and we got 3.45. And from there we calculated Z effective by using this equation, Z minus S. Z is the atomic number of oxygen. So 8 minus 3.45 is 4.55, and the answer was option B. And next one is the effective Z value for p electrons in boron. So for boron, its atomic number is 5, and the electronic configuration is 1s2, 2s2, and 2p1. And from this latest rule, we calculated the S value, that is came to 2.4, and Z effective we calculated as 2.6. And next question was Z effective value for 3D electron in bromine atom. Similar to previous cases, we have wrote down the electronic configuration for bromine, and since we are not we don't have to calculate for electrons other coming after the 3D, we can neglect those, and we calculated screening constant for all these electrons before 3D, and 9 electrons in 3D, and we got the screening constant as 21.15, and Z effective as 13.85. And next we discussed about the decreasing order of ionic radii for given isoelectronic species. So the concept we need to know is that when we have anions, the anions will be having a larger radius, and higher the negative charge, higher the radius. So nitrogen having 3 minus will be the having larger size, then O2 minus, then F minus. And between two cations, the one with the lowest positive charge will be having larger radius, because it will be having lesser effective nuclear charge compared to those with large number of positive charge in the nucleus. So the answer is option C. And next we discussed about this quantum numbers, and uh, how we calculate quantum numbers for uh, the 2s orbital of F atom. So basically there are 4 quantum numbers. Principal quantum number, denotes the electronic shell. So it varies from 1, 2, 3 and etc. And it will have only positive integers. And since we are given 2s, n will be 2. And orbital angular momentum quantum number, and it's represented as L, and it gives the number of nodes in an orbital, and it varies from 0 to n minus 1. For s orbital it's 0, for p orbital it's 1, for d orbital it's 2, for f orbital it's 3. And magnetic quantum number ml, the orientation of it gives the orientation of orbitals ml equal to L2 minus L through 0. That is, if L is 1, we'll have uh, minus 1, plus 1 and 0. And spin quantum number ms, and it gives the direction of electron spin, and it will be either plus half or minus half, and it does not depend on any of the other quantum numbers. So here given 2s, so n will be 2 since it's given, and for s orbital it's 0, uh, L is 0 for s orbital, and ml will be 0, and ms is plus or minus half. And next one is finding bond angles in IF7. So iodine has 7 valence electrons, and 7 fluorine atoms are bonded. So 7 bond pairs are present. So the steric number will be 7, and for 7 the geometry is pentagonal bipyramidal. So if we draw the geometry, 5 fluorine will be in the equatorial plane and 2 in axial. So the angles will be 72 for those in equatorial, and a bond between equatorial and axial will be 90 degrees. So the answer will be option C. And the next question is order of effective nuclear charge. So when we move away from the nucleus, the effective nuclear charge will be decreasing. So basically for 1s, which is closer to nucleus, it will be having highest. Second will be 2s and 2p, because in Slater's rule we consider the rule for both s and p. So if it's in the same shell, both will have same effective nuclear charge, and in 3s, which is further away from the nucleus, it will have lesser effective nuclear charge. So option B will be the answer. And the last one is next one is the correct order of electron affinity for the species N, P, and AS, and it's in the nitrogen family, all 3 elements. And when we move down the group, electron affinity will be decreasing. So arsenic will be having lowest, then phosphorus and nitrogen. And next one is correct order of second ionization energy. And here 4 elements are given: carbon, nitrogen, oxygen, and fluorine. So when we move along a period, the ionization energy increases. So it becomes difficult to remove one electron from an atom. when we move from left to right of a period because of the increase in effective nuclear charge. So first ionization energy will be highest for fluorine, uh, then nitrogen, then oxygen, uh, then carbon, because nitrogen has a half-filled stability, so it will be having higher, and it will require higher energy to remove electron compared to oxygen. So if we are asked for finding first ionization energy, then the order will be fluorine greater than nitrogen, greater than oxygen, greater than carbon. So we are asked to find for the second ionization energy. So after removing one electron, this will be 2p4, 2p2, and 2p1. So it will be easier to remove this electron in carbon, and fluorine also, it becomes easy to remove one electron, but oxygen has half-filled stability now, so it will be difficult to remove that electron compared to fluorine. So the order becomes oxygen greater than fluorine, greater than nitrogen, greater than carbon. So it's option B. And next one is steric number, uh, finding steric number and the lone pairs of pH3. So phosphorus is in the nitrogen group, so it will have 5 valence electrons, and in pH3, 3 bonds are formed. So one lone pair is left. So the steric number will be number of bond pairs plus number of lone pairs. So it's 3 plus 1, that's 4. Steric number is 4, and one lone pair is present. So option is B. And the next one is steric number and lone pairs of IF2 minus. So iodine has 7 lone pairs, but we are given that it's a negative charge. So one more electron is added to iodine. So total of 8 valence electrons are present on iodine, and 2 bonds are formed between iodine and fluorine. So a total of 2 bond pairs and 3 lone pairs are present. So steric number becomes 5. And so the answer is option C, steric number 5 and lone pairs 3. And the next one is geometries of I3 plus and SF2 molecules, where in I3 plus, central atom is iodine, and it's given it's a cation. So there are only 6 valence electrons, and 2 iodine is forming bond between the central atom. So 2 bond pairs and 2 lone pairs. So total of 4 is the steric number. So for the structure geometry will be tetrahedral. And in SF2, sulfur has 6 valence electrons, and it forms 2 bonds between fluorine. So 2 lone pairs and 2 bond pairs. So steric number 4. Same as previous case, the geometry will be tetrahedral. So the answer is both tetrahedral. And the next one is the geometry and shape of xenon bonded to 4 fluorine atoms. So xenon is having 8 electrons in the valence. So and formed 4 bonds between fluorine. So there is 2 lone pairs and 4 bond pairs. So steric number is 6. For 6, we expect an octahedral geometry, and in 6 of them, 2 is lone pairs and 4 is bond pairs. So lone pairs are kept far apart as possible to minimize its repulsion. So we have square octahedral geometry with square planar shape. So the option A is the answer. And here the hybridization of SF6 and PCl5. So in SF6, sulfur has 6 bonds. So to accommodate 6 bonds, we'll need 6 hybridized orbitals. So in sp3d2, we can find 6 hybridized orbitals. And in PCl5, there are 5 bond pairs. So we need 5 hybrid orbitals. So the number hybridization is sp3d. So option C is the answer. Next one is correct order of hybridization of central atoms in water: BH2, HCF2, and F6 2 minus. So first we calculate the steric number for water. So there are 2 lone pairs and 2 bond pairs. So it will be steric number is 4. So 4 hybrid orbitals required. So sp3 hybridization. In BeH2, 2 bond pairs are present. So 2 hybrid orbitals required. So sp hybridization. And in XeF2, we have 3 lone pairs and 2 bond pairs. That is, steric number is 5. So 5 hybrid orbital required. So the hybridization is sp3d. And in fourth case, SiF6 2 minus, there are 6 bond pairs. So steric number is 6. So need 6 hybrid orbital to accommodate all the bond pairs. So the hybridization is sp3d2. And then next question is arrange the chemical species in the order of decreasing radius. So the first one, sodium, magnesium, argon, and phosphorus, they are in the same period, but when we move from left to right of a period, the uh, size of the elements decreases. So the order is sodium, magnesium, phosphorus, and argon. And the next one is I minus, Ba2 plus, Cs plus, and Xe. So we are given isoelectronic species, and we need to know that anions will have larger radius than neutral one, and cations will have smaller radius compared to neutral. So the order will be I minus, Xe, Cs plus, and Ba2 plus. We know that as the charge of cation increases, the size will be decreasing because of increase in effective nuclear size. And the third one is carbon, aluminum, fluorine, and silicon. Carbon and fluorine are in the same period, and aluminum and silicon in the same period. Different, but same period. And when we move down a group, the uh, atomic size increases, and when we move along a period, the size decreases. So from here we can see that since aluminum and silicon are in the period down, so aluminum will be having larger radius compared to silicon, and carbon will be having larger radius compared to fluorine. And in the fourth case, argon, K plus, Cl minus, and S2 minus. These 4 are isoelectronic species, and S have 2 negative charges, so it will be larger anion, and Cl has only 1 negative charge. So S2 minus have larger radius compared to Cl minus, then argon, and K plus will be having smaller radius because it's a cation. And next one is arrange the following chemical species in the order of uh, increasing order of first ionization energy. So ionization energy increases uh, in a, when we move from left to right of a period, and decreases down the group. So in potassium, calcium, and rubidium, potassium and calcium are in same period, and potassium and rubidium in same group. So when we move right, the ionization energy increases. When we move down, decreases. So the order will be rubidium less than potassium, less than calcium. So, and next one is krypton, helium, and argon. So these are inert gases, and helium is on the top of the uh, group, then argon, then krypton. So the order will be krypton less than argon, less than helium. Next one is iodine, xenon, and cesium. So xenon has completely filled configuration, so it's an inert gas, and it's really difficult to remove an electron from a stable configuration. So xenon will be having highest ionization energy, uh, and then cesium will be having lowest because it has S1 configuration. If we remove one electron, it becomes highly stable uh, xenon configuration. So cesium will be having lowest one. And next one is tin, antimony, tellurium, and tin. And the uh, antimony has P3 configuration, so it is half fill stable, so it will be having highest ionization energy. So, and tellurium has a P4. If we remove one electron, it will become half fill stable, so it will be less, having less ionization energy compared to uh, antimony. And so tin will be having even less. And the last question is, what happens to the size of A when it is transformed to A plus or A minus? So when we are forming A minus, we are adding one electron to neutral atom. So an anion is formed. And when an anion is formed, the effective nuclear charge will be low. So the size becomes high. And when we are forming a cation, we are actually removing one electron from the neutral atom. So it becomes a cation with positive charge. So the effective nuclear charge becomes high, and the size of the species reduces. So size of uh, A minus A minus is greater than A, and cation is less than A. So option B is the correct answer. So that's all for uh, today, and in the next week I will discuss about the answers for week 1 and week 2 assignments, um, which has a deadline of 8th February. So after you all submit the assignments, I'll discuss the answer for week 1 and week 2. So if you have any doubts in this set of examples, you can ask. Uh, yes, Prabha. Do you have any questions? Okay. Excuse me. Can you type the question in chat box? Okay. So, Lewis structure is basically uh, if we have an atom and if we have like um, 6 electrons, so uh, and it forms uh, like 3 bonds. Let's assume. So we can say that there are uh, 3 bond pairs and like only 3 electrons. We cannot say how many bond pairs are there and how many lone pairs are there. Like we cannot explain the existence of that one single electrons using that rules. Like if we go to VSEPR, we can find that we can explain it as in the terms of lone pairs and bond pairs, and it actually can define the structures. If we have 8 electrons and it's uh, like this, in VSEPR we have like 4 bond pair and 2 lone pair, so that is 6. So the geometry will be octahedral, and since there are lone pairs, uh, it gives this geometry and lone pairs on the axis. But in if you have a Lewis structure, it cannot actually represent what's the geometry or uh, what will be the shape. It cannot explain all these things, geometry and shapes, with the Lewis structure and these electrons. For example, if NO2 is there, uh, we will say that NO2 has a bend structure because one nitrogen has this 1 electron. Uh, this is an odd number system, but it's with Lewis concept, it won't be possible to say this is the structure, or it cannot talk about the bonding present. Is it clear? Do you have any other doubts? If not, we can close the session. Uh, Next week, that's next Saturday, I'll be discussing about the answers of assignment 1 and 2, and maybe some week 2 lecture materials as well. So thank you for participating, and see you next week.